Okay, so we were looking at the surface gravity of black holes, and a way of defining this was to say that Ka del A Kb is plus or minus kappa times Kb, and we manipulated this expression into the following one, which is easier to use: minus a half Kb of Ka is equal to plus or minus kappa times Kb, since K was a killing vector. Now let's think about evaluating this for the Schwarzschild metric. Remember that the entirety of the Schwarzschild metric looks something like this. Try to do this calculation using defined in t r theta phi, going in this direction towards where you think the horizon is, and that will of course get you into a mess because the coordinates don't work there. What look 0, 0, and in VR theta phi coordinates, well, let's call these primed coordinates so that we don't become confused. The components of a vector Ka prime will be equal to A prime A Ka, where A prime A is the matrix of the derivatives of the new coordinates with respect to the old ones. Since you go from tr theta phi to vr theta phi by the following transformation, v is prime is t plus r plus 2m log the modulus of r minus 2m. R prime is the same as the old r, and we don't really care about anything else. It obviously follows that k of v prime, that's equal to a v prime t kt, is going to be 1, 0, 0, 0. Sorry, it's 1. Similarly, all the other components are 0, so k a prime in the VR theta phi coordinates is 1, 0, 0, 0. However, you have to be a bit careful about this, because if you lower this index, you will get some slightly different things that you might not have expected. Remember, we do need to know what Kb is with a downstairs index to be able to do this calculation. So, remember that in advanced Eddington-Finkelstein coordinates, the metric looks like minus into 1 minus 2m over r dv squared plus 2 dv dr plus r squared into d theta squared plus sine squared theta d phi squared. So Ka with its index downstairs in Vr theta phi coordinates is going to be equal to 1 minus 2m over r with a minus sign, and then there'll be a 1, 0, 0, which might not be what you expected. Now we can carry out the calculation. K in the Vr theta phi coordinates. What is Ka, Ka? I'll drop the primes from now on. Well, that's easy, it's just minus 1 plus 2m over r. So the left-hand side of this equation reads minus 1 half d by dr of Ka, which is minus 1 plus 2m over r, is equal to plus or minus kappa times 1. And that's the radial component of that equation. The other ones don't give you anything. Evaluate this at r equals 2m. Well, d by dr of minus 1 is nothing. D by dr of 2m over r is minus 2m over r squared. So this turns into m over r squared is equal to plus or minus kappa. And so at r equals 2m, the only place we're interested in, kappa is equal to 1 over 4m. So that's how you calculate it. If you attempted to do this in tr theta phi coordinates, you will end up in a mess. You'll discover something is complete nonsense, largely because the coordinate system that you would use breaks down at the place that you want to use it. So this is an example of having to be careful about how you do a calculation. So this you do because the Schwarzschild coordinates don't work. I advise trying it using Schwarzschild coordinates just to see what does go wrong.
Is the plus and minus?
I wanted kappa to be positive. If you used my conventions and you evaluated kappa here, and you forgot about the plus or minus, you would end up with minus 1 over 4m. But it's still positive. Well, I suppose you could argue that it wasn't positive because you tend to get thrown out of the horizon. But kappa is usually taken to be positive. So one can imagine doing this calculation for the Kerr-Newman sequence of solutions. It works in the same way. Again, you have to use coordinates which work on the horizon. You will discover that kappa is equal to the square root of m squared minus a squared minus q squared divided by 2m squared minus q squared plus 2m times the square root of m squared minus a squared minus q squared. The first thing you'll notice about this is that provided the black hole actually exists, namely that m squared is greater than a squared plus q squared, this thing is positive and you don't have to worry about the signs. So this thing is well defined as long as you don't have a naked singularity. So that's good. However, you'll notice for the extreme solutions, which I think is what we called class 2, where m squared plus a is equal to a squared plus q squared, kappa tends to 0. Well, it equals 0 if m squared is a squared plus q squared. That's a reflection of this rather strange degenerate case where you had coincident inner and outer horizons. The second thing, so there's something pathological about the limit k equals 0, something a bit strange about it. The second thing that you will notice about this is that kappa 2 does not depend on where you are on the horizon. It does not depend on the latitude theta. It did not have to be independent of theta. It could have come out to be theta dependent, but did not do so. This result is sufficiently important that it has a name. It is usually called the zeroth law of black hole mechanics. In case that seems strange in itself, the reason it is called the zeroth law of black hole mechanics is because there is a precise correspondence between the laws of black hole mechanics and the laws of thermodynamics. We will discover that kappa looks like a temperature towards the end of the lectures. We have not discovered it yet. If you take an object that is in thermodynamic equilibrium, its temperature is constant. So, the analogous statement here is you take a black hole which is stationary, namely the Kerr-Newman solution, compute kappa, and discover it does not depend on where you are on the surface of the black hole. That's analogous to saying that the temperature is constant. For that reason, this is called the zeroth law of black hole mechanics, from which you could guess that there's some other laws of black hole mechanics which also look like the laws of thermodynamics. We will meet all of the other, but we can meet the third one right now, actually. If you really thought that kappa was a temperature, then kappa being zero, being strange, is basically the same thing as the third law of thermodynamics. So you could say that this was the third law of black hole mechanics, but you have to be extremely careful about that because the logical foundation of the third law of thermodynamics is a bit shaky. So, as you can see, we're now missing the first and second laws of black hole mechanics. So let's look and see what we can discover. So, we've got as far as defining a surface gravity. What are the other things that you can define? Oh, and an angular velocity. What are the other things that you can define about this black hole? Well, one obvious thing you can define is the charge. Suppose that I gave you a section of some space-time at t equals constant surface. So this is space. And I said to you, evaluate the charge inside some region. So here is a big sphere at infinity. None of us would have any difficulty in writing down a formula for the charge inside that sphere using Gauss's law. So what you would do is to say, well, that's just the integral of E dot ds. I don't want to write it that way. I want to write it using four-dimensional covariant language. So this is a two-dimensional surface. So it can be written as having surface area element dsAb. And if I'm going to write down the charge, I have to integrate the field strength FAB over this surface dsAb. And this will be over a sphere at infinity. There is a conventional normalization factor which is 1 over 4 pi. Yes, 4 pi. Yes, 4 pi. And that defines the charge. To see that that really is the same as the integral of E dot ds, just think about dsAb. This is a two-dimensional surface. A and B are the normal directions to that surface, so these are in the t and the r directions. So if that's t and r, that's t and r, and the tr component of FAB is just the electric field in the radial direction. So this is just Gauss's law, and so one would have no real difficulty trying to evaluate that. Let's do it for the Reissner-Nordstrom solution and make sure that we do get the right thing, and not 4 pi times the right thing, or 80 pi or something. You can do it for Kerr as well if you want to, but it's a bit harder. So, let's see. The only interesting component of the electric potential is Q over R in the time direction. So this is in the Schwarzschild metric. That means the only interesting component of FAB, that's DAAB minus DBAA, and that is going to be equal to, well, F. Well, this is the T component, so let's compute RT. That's going to be minus Q over R squared. And the only other non-vanishing component is FTR, which is plus Q over R squared. So the radial component of the electric field is exactly what I said it was, namely Q over R squared. Now let's evaluate this surface area element. DSAB is equal to 1/2 of TARB d sigma, where these are the unit normal vectors to the sphere at infinity. T is going to be the time-like one. R will be the radial one. And out near infinity, you can just take these things to be 1, 0, 0, 0, and RA to be 0, 1, 0, 0, because the curvature does not matter to us out at infinity. Then what we do is we just simply calculate this thing. D sigma is going to be sine theta d theta d phi times an r squared. In other words, the determinant of the two-dimensional metric you get by putting t and r equal to a constant. And the whole thing is therefore going to give me one over 4 pi FAB dsAB. That's going to be 1 over 4 pi times the integral of FTR dSTR twice, because when you do the sum you get the TR component and the RT component. That turns out to be 1 over 4 pi, 2 times a half, TATB gives me nothing, Q over R squared from FTR dSTR is R squared sine theta d theta d phi, which I integrate over the sphere. And this, of course, first of all, doesn't depend on the radius of the sphere, but is equal to Q. So this does indeed reproduce the charge, as promised.
Obvious from Stokes?
Yes. There is a reason why I did that. Similarly, you can define an electrostatic potential. Take the Killing vector d by dt. So it's a Killing vector associated with time translation. That's a nice way of picking out what K is. So I can define the electrostatic potential phi to be equal to KAAA. that it finds electrostatic potential everywhere for a space-time that is stationary or static. So this is just equal to Q over R. Not very surprising. So were you to have a black hole sitting here, as far as electric field is concerned, you will be able to move this surface anywhere you wanted to, down to the horizon, and conclude that the charge just simply lays somewhere inside the horizon, but you wouldn't actually know where. So this thing you can say certainly has charge Q. And you could also associate an electrostatic potential with the horizon, rather like you would for a capacitor if the thing was just some big blob. It's just Q over R. So that's electrostatic potential. You can call that the potential of the black hole. Q over R evaluated on the horizon. That's very easy for the Rice-Nordstrom metric, but a bit more unpleasant for the Kerr metric. Were you to evaluate this for the Kerr-Newman's metric, we would discover that phi is equal to Q into m plus the square root of m squared minus a squared minus q squared divided by 2m squared minus a squared minus q squared plus 2m into the square root of m squared minus a squared minus q squared. Something which also is independent of the location on the surface of the black hole. So that's electrostatic potential. Now, in some ways, gravity is very like electromagnetism. So you might say, well, if I can define charge like this, perhaps I can define mass in a similar way. Now, of course, there are many ways you can think about this. But a very simple way of thinking about it, well, actually there are two ways of thinking about it. Let's go back to thinking about it in terms of the gravitational field at infinity. One way of thinking about mass is to say that the gravitational field that you experience out at infinity has got to look like the gravitational field of a Newtonian object of similar mass, and therefore that's a way of describing the mass. We could call that the gravitational mass, if you like. On the other hand, another way of thinking about mass is it's the self-energy of something, and that's probably more appropriate to thinking about the mass of a black hole. That's because it is, after all, concentrated in some particular region of space-time. The black hole is a solution of the vacuum Einstein equations outside the horizon, and is peculiar inside the horizon. So we might be better off thinking of not so much what it does at infinity, but try to invent some local characterization of what the mass is. But we know that there are only conserved quantities in general relativity if you have killing vectors. So if you're interested in energy or mass, you're interested in things like killing vectors of time translation. And so you can use that to describe the mass of a black hole. So this is originally due to Komar, and it's called the Komar integral. And he thought, incorrectly, but nevertheless plausibly, that the mass of some space-time could be described by a surface integral rather in the similar way to the way in which you can describe the charge of something. So he wanted to have this thing integrated over a sphere at infinity, and he wanted to think of this as being rather like a Gaussian integral for the charge of something in electrostatics, but here it worked for the mass of something in general relativity. So he called this we'll call it the Komar mass, m sub k. Now, to be fair to him, this is not completely crazy. Let's first of all evaluate this thing in the Schwarzschild metric. To make life easy for ourselves, it's pretty easy. The time-like killing vector Ka in Schwarzschild coordinates is 1, 0, 0, 0. So if you lower the index, you will end up with minus 1 plus 2m over r, 0, 0, 0. If you're interested in calculating del A kb, the only bit of this equation which will survive near infinity is the bit that looks like dr of kt, and that is going to be minus 2m over r squared. So that certainly looks like the right kind of thing, and if you evaluate this integral, you will end up with mk is equal to m, rather in the way, similarly to the way in which we did it for a Gaussian integral in electrostatics. Now, why should we believe that this has anything to do with mass? There's a simple argument which you can derive just by playing around with the Einstein equations. So let's think about what we're doing here. I shouldn't have rubbed off that picture. Let's suppose that there is no black hole for the time being, but just some distribution of stuff here. Galaxy, Centre for Mathematical Sciences or whatever. Mk, we say, is equal to 1 over 4 pi times the integral over the sphere at infinity of del A kb dsAb. Now use the divergence theorem.
I know this is problematical because you have just a random distribution. It's not going to be static. You're not going to have a time-like killing vector. You don't have that integral somewhere.
Oh, well, it works perfectly well for the Earth, and the Centre for Mathematical Sciences is quite static. It's true that if you had gas or something like that, it probably wouldn't be.
If you had a system with black holes that wasn't static, you also wouldn't have a killing vector. We'd not have charge.
True. I will do that. I will do that problem later.
Okay.
So if you apply the divergence theorem to this, and your sphere at infinity was out here, so this is my S2. Application of the divergence theorem will turn this into an integral over all of space enclosed inside the sphere. And the divergence of this thing. So it will be del A kb d sigma b, and with my sign conventions, a minus sign stuck out the front, because if I have these things and I integrate by parts, that's what I get. The minus sign is just, it's not an artifact, it's just a consequence of my conventions. It might not be the same as Dr. Stewart's conventions. Now, because k is a killing vector, you can evaluate box of k. Killing vectors obey Killing's equation, del A kb plus del B ka equals 0. If you want to take the divergence of that, del A kb plus del B ka is equal to 0. This term is what we've got here. This term we can transmute into something nice. Were we to commute these derivatives, you'd end up with del B del A ka. In other words, a gradient of the divergence of k. But if you stare at this, you can see that contracting this with GAB will tell you that divergence of k is equal to 0. So commuting these derivatives will give me a term involving the curvature. And you will end up with del A kb plus R A B A C kc plus del B del A ka is equal to 0. So that thing is 0 by Killing's equation. This thing is really, however, just the Ricci tensor. So we end up with that. But you can reorganize the Einstein equations. RAB minus a half R GAB is equal to 8 pi times the energy momentum tensor. If you take the trace of this equation, you'll end up with 1 minus a half times 4 times R is equal to 8 pi times the trace of the energy momentum tensor. So this can be rearranged as RAB is equal to 8 pi into TAB minus a half GAB times the trace of the energy momentum tensor. Substituting it in for the Komar mass gives you the integral over sigma, 1 over 4 pi, a minus a Ricci tensor term, box, but there's another minus sign there, so I'll end up with R, B, C, K, B, D, sigma, C. So that's the integral in question. This thing I can take to be parallel to K. Oh, wait a minute, I need to substitute this in first. So I end up with integral over sigma of 2TBC minus GBCT KB d sigma C. So in that sense, it's sort of what you want, because this thing is the integral of some energy momentum tensor over the surface, and at some level is going to count up the mass. If this thing is parallel to C, then this is really, then both of these things pick out the time component of this thing, so you're basically picking out T00 minus G00 times the trace. So this formula says that the mass is the integral of something to do with the energy momentum tensor. What quantity is it actually? The The easiest way to see what it actually is of course to substitute in what you expect from matter with energy density ρ and pressure P. Then you would say that TAB was P plus rho UA UB plus P times GAB, UA being the fall velocity of what the matter in question.
In what sense is a system with non-vanishing pressure static?
Sorry, non-vanishing?
In what sense is a system with non-vanishing pressure static?
Well, let's take the Earth, for example. That's pretty static.
Pretty static. We're using some really nice properties of static solutions. Almost static isn't the same.
The Earth is static on a time scale of the order of, it's known to be static on the time scale of 4.5 billion years, and presumably a bit longer than that. So it doesn't worry me too much. What would worry me a whole lot more is vast deviations of staticity, like, for example, two colliding black holes. But since I can deal with that case, but not this way, I'm going to stick with this. To see what this integral is, just look at an orthonormal frame. You're going to pick out the 0, 0 component of that thing in brackets there. Well, T0, 0 in an orthonormal frame, well, TAB in an orthonormal frame is, of course, we all know, rho, and then pressure times delta Ij. So the trace of the energy momentum tensor, T, is equal to minus T0, 0 plus Tij delta Ij, and that is equal to 3p minus rho. T0, 0, on the other hand, is equal to rho. So this thing that you've got here, if you evaluate its 0, 0 component, two times T0, 0, that's 2 rho. So that doesn't look great. Minus G0, 0, that's minus minus 1, so it's plus. The trace of the energy momentum tensor is 3p minus rho. So the whole thing is rho plus 3p. That's kind of familiar. Think about the Raychaudhuri equation in cosmology, where you find energy density, you always find rho plus 3p. Here is another example of it. You find rho plus 3p is the source of the gravitational field yet again. So you feel very happy. This is a sensible definition of mass, provided the space-time is static. However, there's always mass because you can always describe a gravitational field at infinity if you're asymptotically flat. So there is obviously something missing from this whole description of what's going on. For the moment, let's not bother about that. But just note that there is something definitely not quite right here. Angular momentum I can do in much the same way. Angular momentum is associated with rotational symmetry. So if I have a killing vector, m, what did I call it? Probably called it r, didn't I, for rotation? Never mind. So this corresponded to rotations about some symmetry axis. Then I can define a Komar angular momentum, J sub k, which is equal to the integral of del A mb dsab over a sphere at infinity. And to get my conventions right, this involves a factor of 1 over 8 pi. So this is the angular momentum defined in a similar way. I do not wish to do this calculation, so it's on the example sheets. For the Kerr-Newman solutions, you'll discover that Jk is equal to A times m. So what we have done is to have some idea about angular momentum and mass as a result of all of this, perhaps defined in a similar way to electric charge. So having said that, I can now do a simple thought experiment. Here is a black hole of mass m, charge q, angular momentum j. That's all I need to know about it if it's sitting in asymptotically flat space-time and is in equilibrium. I can compute from this the area of the event horizon. That's just a geometrical quantity, the integral of the thing at constant t, the surface gravity, the angular velocity, and the electrostatic potential. All of those, of course, determined by m, j, and q, because that's all there is. And now what I do is I imagine that's because Kerr-Newman solutions are the only things that are only solutions you've got. And so what I do is I throw something into the black hole and wait for it to settle down. I don't throw in much, so this is an infinitesimal change, which turns n to m plus dm, q to q plus dq, and j to j plus dj. And I wait for equilibrium to be restored and ask what exactly has happened here. Well, the area of the event horizon will have changed, as will k and omega and phi. But I know that if this thing is a Kerr-Newman solution, the only thing that's happened here is you've re-equilibrated, everything is going to be independent of time again. This is another Kerr-Newman solution. So, I can now carry out the following calculation. And you will discover something miraculous happens. Let's consider A, the area of the event horizon, as a function of m and j and q. If I carry out the variation as specified here, then from the chain rule, the change in the area is equal to dA by dm at constant j and q times dm plus dA times dj at constant m and q times dj plus dA by dq at constant m and j times dq. And I can evaluate all of those partial derivatives because I know the area of the event horizon. And if you have forgotten the area of the event horizon, I will tell it to you. It's just 4 pi times r plus squared it's the proper area at fixed t for r on the horizon, or r and theta. For the Kerr metrics, this is equal to 4 pi into m plus the square root of m squared minus a squared minus q squared. So now you can go ahead and calculate all of these objects. You can calculate dA dm. At constant j and q. If you do this, you will discover something miraculous, that this is in fact 8 pi over kappa. That looks like a coincidence, because after all, this is a geometrical calculation involving the mass, whereas kappa is something peculiar to do with null geodesics close to the horizon. This you just calculate from the properties of the Kerr-Newman metric. If you calculate dA dj at constant m and q, you will discover that this is equal to minus 8 pi omega over kappa. And if you calculate dA dq at constant j and m, you will discover this is a minus 8 pi phi over kappa. Well, that just looks like some fluky result from looking at the Kerr-Newman solutions. The original way this was done was not this way. It was done in an entirely different way, based on more general arguments. But since the Kerr-Newman solutions are the only solutions, at least if you're asymptotically flat, that are stationary or static, this is good enough. Let's rearrange that formula. Sticking it into the thing on the left tells you that dA is equal to 8 pi over kappa times dm minus 8 pi omega over kappa dj minus 8 pi phi over kappa dq. Now what you do is you multiply by kappa over 8 pi and write this in the form dm is equal to something. What do you get? Well, you get kappa dA over 8 pi plus omega dj plus phi dq. This result is sometimes called the first law of black hole mechanics. For the simple reason that it looks like the first law of thermodynamics. The first law of thermodynamics says if you make an infinitesimal change to the system and calculate the change in energy, that's dm, it's equal to the change in the heat plus the amount of work done. These two terms are obviously work terms. Phi dq is what you would have to expend in energy to change the charge of something by an amount dq if its potential was phi. Omega dj is the amount of work you'd have to do if you wanted to change the spin of something of angular velocity omega by changing the total angular momentum by j. This term looks unfamiliar. This would, of course, be the same as the first law of thermodynamics if you thought that this was TdS. Of course, that makes no sense whatsoever, because T is 0. You know that T is 0 because if you stare at a black hole, nothing comes out. including black body radiation, so you conclude its temperature was 0. So this can't be TDS, or at least so classical reasoning would tell you. So this is not quite the same thing as the first law of black hole mechanics. Well, let's see. We should probably stop there and contemplate that over the weekend.